Our presentation today is about two West Coast buildings, not your everyday design projects. And our presenter is Andy Metten from Bush Bohlman Partners. If you have any questions during the presentation, please feel free to leave them in the chat box, or you can use the raise hand feature and we'll let you speak. Before we begin, I just want to take a moment to thank all of our Steel Center members. And then I want to show you where you can find previous presentations that we've had before. And after this presentation, I'll send you a follow-up email with the recording of this presentation if you would like to rewatch it. So to tell you a bit about Andy, he doesn't need an introduction, but Andy is a practicing structural engineer and partner in the Vancouver-based engineering firm Bush Bohlman Partners. For almost 40 years, he has worked on the design of several buildings and bridges, including the Vancouver International Airport, the Nassau, Bahamas Airport, and the SkyTrain Fraser River crossing at Westminster, to name a few. Andy has graduated from the University of British Columbia with a bachelor's in civil engineering and a master's in structural engineering. And ever since he graduated, he's been practicing in structural engineering. Andy is also a member of a couple of different committees in NBCC and the Design of Steel Structures S16 handbook. And he's also the co-author of the widely used Structural Steel for Canadian Buildings Designer's Guide book. With that, I will hand over to Andy and I'll let him take us on the journey of these two buildings.
Now, do I have a share screen icon somewhere?
Yes, so that should be on your Zoom. Can you see it at the moment?
Yeah, there we go. Share screen. And I want to go to this guy. And I want to okay, it's nice to be back. Thanks for inviting me back again, and it's a pleasure to be here. It's one of the things with COVID is that we get to do things like this. There's lots of things we can't do, but this has made it possible to do things like this, and we now can do lectures from our home and without having to travel large distances and increase our carbon footprint. So today I've got two what I think is interesting projects, and hopefully you'll think they're interesting by the end of it. And I want to discuss both those projects from 3 points of view. Why are these projects being built? Why was steel chosen? And a variety of conceptual design considerations. And I'm going to focus on the steel aspects because this is steel for lunch and how to do them. So the first one of these is the Masset Tsunami Tower. And this is actually north of Edmonton. And you might have a hard time believing that, but you're at 53.5 north and this is at 54 north. So, and I'm down here at 49, almost at the US border. And this is where the project is. So what's a tsunami? And Hollywood's given us lots of versions, and fortunately, it doesn't actually look like this in reality. And this is, it's in some ways, it's like the tide coming in very quickly. Tsunami waves move very, very quickly, but they tend not to be that huge overcresting wave that you saw in the Hollywood pictures. And this is from the Sendai earthquake in Japan. And if we look up here where my pointer is, this is 5736. About 4 seconds later, what about, we got 9 seconds later, we're almost 20 seconds later here. So this water is moving very fast, but it's not a huge overcresting wave that's coming in. And here we see basically a, sort of about 40 seconds later, what was bare ground is now totally covered with very rushing water that's coming there, but it's not, and you can start to see things are shifting around. This white box here is starting to move closer, and things get moved around by the earthquake. So here's a view of the Sunday earthquake, Sunday airport, and the wave hit the airport about 11 minutes after the earthquake happened, and it went for several kilometers inland. And the solution is to get somewhere high that isn't going to collapse under the earth, under either the earthquake or the tsunami. So what causes tsunamis is that we're having a subduction earthquake in which one plate is going over another one, and they kind of get stuck. So what is happening is we start off like this, and then the plate kind of goes like this, and then all of a sudden it kind of flicks. And so when that flicking motion happens, the tsunami starts to happen, and it's very rapidly can arrive on land, or it can take several hours and arrive on a different continent. But our project site, we have down here a big subduction zone that goes up and down the West Coast and eventually heads down into Oregon and California. And here's our project site. So the waves from that come along, and then they are coming in, and they're arriving in this estuary here, and the volume of water here is crammed down, and here's our site right here. So our water level is going to rise. So what happens now? There's an earthquake. The school gets a tsunami warning. Everybody tries to jump into available buses and cars and things like that. And they travel 10 kilometers, mostly along this side of this estuary at the same level that's going to get inundated with water, up to a safety zone here. And past attempts at this with real tsunami warnings have resulted in it taking about 40 minutes. Unfortunately, the tsunami may arrive as quickly as 3 minutes to the site. So the people that are escaping here are not going to be safe. So the school is basically at about 5 meters above the high tide. The tsunami safe zone's about 10 meters above the high tide zone. So what we're going to do is build a structure here that people can climb up to and escape from the tsunami. The tsunami will rush underneath them, and they would be safe and basically watching this event that they're going to remember for their entire rest of their lives, because it is going to be very dramatic, but they're going to be alive to remember that. And in doing this, we're going to make sure that this is used for other things, and by other things, what we're going to do is have a basketball court underneath so that can be used for that. So tsunami vertical evacuation, there's a lot of examples in Japan where this is structures have survived the tsunamis. Sometimes, if they're not very tall, you can wind up with lots of sort of damage to finishes, but you can see here the steel structure, and here's a concrete structure, both of which have done quite nicely. And if you were, I'm not sure where the water came to, but presumably it went over this one, and you'd need to be standing on the roof for this. Here you can see these folks that they've come up here, and the water level looks like it's come somewhere into there, and they're safe up there and awaiting a rescue. And there's lots and lots of these tsunami towers in Japan. If you travel by train, You see them along the coastal areas, and you kind of wonder if there was a tsunami warning, would the train stop and let everybody climb up these, or would you just get sort of inundated and washed away like people did on a train in Sri Lanka after the Sumatran subduction event. Here's an example of an earthquake that happened in Anchorage back in 1964. Was a large earthquake, and it sent out a tsunami which went down to Port Alberni on Vancouver Island and did lots of damage. The advantage was that there was lots of warnings for this, and people escaped lots of property damage. But there are warning sirens in Port Alberni, and now if you go to Port Alberni, you'll see all the tsunami escape route signs well labeled, and you can see the tsunami warning signs. And the aim is to get people out of the danger zone, and that's what the tsunami tower does. So the school is being seismically upgraded as part of this process, and we're going to put on the basketball court a freestanding tsunami tower, which will allow for people to evacuate. So we've done a conceptual design of this. We've done project definition report drawings, which can be priced by a quantity surveyor. And basically, we've got this as a moment frame structure to give as little surface area for the tsunami wave as possible. And in order to design these structures, we wanted to be able to design them twice. So first thing we have to do is make sure that it survives the earthquake. And earthquakes and wind are both quite high on Haida Gwaii. Some of the two largest recorded earthquakes in Canada have both occurred on Haida Gwaii. And it also needs to be able to withstand the forces from the tsunami on water and debris flow. And so there's a variety of references available for the water force. If you're interested in this one's free from FEMA, and you can download it very easily. This one's about $130 from ASCE, and which is probably 130 American, about 250 Canadian. And so we wind up with this, these sort of guides, and there's lots in this book here. There's lots of worked examples, and the FEMA guide also has some loads. And what we have is a hydrostatic pressure and a hydrodynamic pressure. And it's not wildly different from designing a pier where you've got waves coming in and water coming in, and maybe at times you have absolutely nothing here. It's maybe the tide's out and then the tide comes in. But those are the kind of conditions that you have to design the tsunami tower for, as well as the earthquake load. So our design for seismic follows normal procedures, and we have a moment frame, and we have cruciform columns, and which are shaped like a wide flange with two T's welded in. And we've done those an awful lot. We did them on the Bahamas airport. We did them on the Vancouver International Airport, and they work really well because your moment frame now has stiffness. The columns have stiffness in two directions. So you wind up with a very balanced seismic system looking like this, and it will work well for seismic loading. So why steel? We have a very remote site. We're up here. If you wanted, our fabrication plants are down here. If the one way to get there would be to put them on a truck, put the pieces on a truck, and these are all truckable sizes, drive them all the way up here to Prince George, then head over here to Prince Rupert, and then they could come across on a ferry, actually down to here, and then they'd be driven up to here. That's one way. They could be barged up from Vancouver, would be another solution. There are ferries also that they could drive up to here, and then there's a ferry that goes up to Prince Rupert, and then it could come over here as well, and then driven up again. But it's basically a tough site to get to. And while it's tough for steel, it's even tougher for concrete. You've got very tough building formwork and rebar and all those sort of skills necessary to do that in a small community. So, and there's certainly no steel fabrication plants in the community that could handle this. So it's got to come from a distance, but there's also limited ability to produce concrete and limited ability to do the formwork. So where is the project today? I've been in conversations and we're supposed to start our detailed design soon, and geotechnical studies are going to happen soon. And so they're aiming for construction start summer of 2022, which is not this coming summer, but a year from now. So we feel we'll be well able to provide design by that time. So let's move on to the other topic, which is the TRUIMF IAMI, which is a bit more like a traditional building. And I'm saying here, we've been working on it for the past 3 to 4 years. It's now getting a bit longer than that. It's an interesting building. It has processes that are an important part of the building, and hopefully you'll find something interesting here. So it's located on the UBC campus, and this is the site. And IAMI stands for Institute for Advanced Medical Isotopes. And this is downtown Vancouver, and I live down here. So you can get to here or to here. I can get from my house here to work here in about 30 minutes on my bike, 35 minutes. And I could get to this at about 35 minutes on my bike, but I usually drive because I got my safety gear. So this Institute for Advanced Medical Isotopes looks like a pretty normal looking building. Why are we so interested and excited about it? And the story is we've got to really look at medical isotopes. And Canada is a world leader in the production of them. And they were originally produced from the Chalk River reactor. And it ceased production in October 2016. And the reactor was closed down. And then what happened was that the production of medical isotopes became a part of cyclotrons, which are scattered across the country. And so there's now several medical isotopes, and they're used for imaging for cancer cells and treatment of cancer cells. And the medical isotopes that are going to be produced from IAMI are believed to be a really silver bullet for cancer. So we're very optimistic that this is going to do good things for treating it. So there's 3 ways to obtain radioactive isotopes. You can get the naturally occurring ones. They're hard to get. There's not much choice, and they have a half-life decay pretty easily. So that's kind of out of the question. There's a nuclear reactor such as Chalk River, and those are kind of getting shut down, and there's very few that are in a position that they can produce the medical isotopes. And there's synthetic means such as a cyclotron. And this is where the IAMI project comes into being. And so there's a variety of these that are scattered across the country. And the advantage with that is that you wind up having the source of your medical isotopes fairly close to where you need them. These things do have a half-life, and you can look, there's some references there you can look at more if you want to find them. So from our point of view, what's the structural engineering perspective of them? One is that you've got an expensive machine that needs to be on a rigid base, so thick slabs required. And the next one is we've got thick concrete walls and slabs over and below required because you've got radioactive. And you can't let the shielding become radioactive, so you've got exotic concrete mixes. And I'm not going to concentrate too much on the concrete mixes because this is more of a steel lecture. So the cyclotron weighs 28,000 kilograms. It needs a lot of power. And so you wind up with a lot of weight. And just to give an example of what it weighs, I drive a 2014 Nissan Altima, and I would need 20 of those to equal the machine. One loaded concrete truck, or this is the one that I like the best, a fully loaded Q400 with 90 passengers and crew, fuel and cargo. So basically the cyclotrons are heavy, right? So you got to be able to get them in and out. If there's a problem with it, you got to be able to get it out. And hopefully that won't be the case, but you definitely have to be able to get it in. And you also have to have something that's not going to collapse when you sit it on there. So what are we trying to do? We're going to do conceptual design. And in conceptual design, we scope out the project and we develop a project definition report. And the client wants to see what they're getting and what it will cost. And by this project definition report, we're going to put all of our member sizes and things like that so that we wind up being able to label things and costs. So project has a variety of stages, and we're going to talk about this conceptual planning stage. And so at this stage here, you've got the most ability to influence the project. And you want to do a variety of your work and figure out a lot of your problems at this stage, because the changes are almost zero cost to make those changes. And whereas if we wait till too late, projects under construction, we say, no, we got to change those beam sizes, you're not going to be very popular. So we start out here with conceptual design. The effective change is no change costs expected, really. And during the fabrication erection stage, you've got lots of credibility problems, and it's definitely the most expensive. So let's look at the conceptual design and design development stages and look at how we get our answers for those. So we're gonna start off with before our working drawings, but we should have, by the end of we've finished our conceptual design, all the structural elements positioned and sized. We want to have lots of information on there so that when the quantity surveyor does his takeoff, he does a takeoff at the end of conceptual design and then maybe at the end of design development. But we don't want the price going into the client and there's been a huge jump in structural costs. And why is there this huge jump in structural costs? Why didn't you pick these up in conceptual design? So I've been down that road before, and I tend to want to do lots of effort in the conceptual design phase to get what we want. So let's look at what we need to start it. We need the configuration of the building, and that's mostly given to us by the architect or the owner. And the constraints on the building, again, mostly given by the architect and owner. It must meet code, it must meet budget, and it must satisfy the loading. So we need to find out what the loading is. So we determine the configuration. The architect's going to give us this. We have the configuration of the cyclotron area and the caves. And this is where we have the cyclotron. And because it's emitting radioactive material, we have what's called a caves and a maze to get in there. So these are the target caves, and the cyclotron produces a beamline of angry atoms that go on point in here at the target. And in order to get in there, you go through this maze, and obviously you're not going to be going in there when the beamline is active. And through here, we wind up, this is a maze. So none of these angry atoms have a straight line access to an outside world. So money's always a constraint. You need to be efficient in your design. You've got to strive to keep the building area down, because costs are very much related to building area. And cost is going to influence your choice of material and your structural form. And you want to be stressing ways to save costs diplomatically. You know, you don't want to say, hey, you know, this architectural design is absolutely awful. You know, and particularly in front of the architect, you want to do this in a diplomatic way and detail and coordinate your drawings to reduce the extra costs. So lots of types of radiation that result in thick concrete, and our shielding parameters done by simulations from TRUIMF themselves, and they present us with this and say how thick the walls need to be and give us some indication of the properties. And there's lots of interesting concrete in this building. And then they give us sort of dimensions here, and you can tell these aren't actually by structural engineers, because you're getting millimeters to the nearest millimeter and things like that that are very tough to build. And you sort of take a look at these and say, well, can we make this, the red ones, the same dimension? They sort of seem to be the same thing. And then you sort of get some rationalization. But one of the things that thought about, well, why don't we do the speed core steel plate shielding? And had been to a speed core lecture, and this is a very popular topic right now, and it's formworks made off site, thinner concretes, steel, as steel does some of the shielding. Can we get by with that? And but steel's okay for some of the radiation, but it becomes radioactive when it's exposed to neutron radiation. So what we really need is concrete containing boron, because boron can handle that radiation. And we couldn't do the steel shielding that seemed like a good idea at the time, but can't win them all. So getting the cyclotron into place, you're going to need a fairly heavy crane, but we also need to make sure that we've got a way of getting it in. So the building stretches up here. There's a setback here where they are two lids. And these are our two lids. And what we made the lids out of was we used steel on the lids. This was where we weren't worried about the radiation, the gamma radiation, but we were still worried about radiation of various forms. And we wanted to try to make the lid such that it could actually be lifted out without using a heavier crane for the lid than we needed for the cyclotron. So we made the lid in two lifts. And so we've got concrete parts with nice corbel designs and steel and concrete filled lids over here. So what are our constraints? One of them is that we need to figure out what our loads are. We don't want to design for loads that are too high. We don't want to design for loads that's too low. And we always have loads from two sources. We have loads for our occupied areas, which are vertical loads, and then we have our environmental loads, which are our snow on the roof, our seismic load, and our wind load. And loading's always a balance. If you design for loads that are too high, the building costs higher. If you design for loads that are too low, the owner can't use the building in its intended use. And some parts of this building are going to have incredibly heavy loads like the cyclotron on it. Other parts are going to have lead blocks being brought in for shielding on our ground floor, and hot cells which have a lot of shielding and weight from that in there. So we need to make sure they're happy. So what load to use for our upper floors for our steel part, and there's lots of options, but none of them that really apply to laboratory. So there's various ways we could look at: equipment rooms, mechanical rooms, 3.6 kPa, that's way too low. Office areas and above, 2.4, that's again way too low. Operating rooms and laboratories, 3.6, and that may work for some labs, but certainly not those with lead shielding. And so the code specifies mechanical rooms at 3.6 kPa. And if you tried to defend yourself by saying, well, that's what the code says, so that's what I'm going to design to, you've got a very unhappy client. So we need lots of housekeeping pads. We need a generous allowance for heavy equipment. There's lots of sort of HEPA filters and variety of other sort of heavy duty mechanical equipment that goes into these rooms. So we do a variety of load sheets that come along very early in the stage of the project. And if you want to learn more about load sheets, they're in Bob Driver's book. And so our drawings contain loading information at each level. And we also show the total dead load as required by BCBC 2018 and NBC 2015 on there as well. So there's load diagrams that are on there showing what we've designed everything for. And again, it must meet code. And we had a bit of a debate at the start of this project as to which code we were going to follow, whether it was the British Columbia Building Code 2012 or 2018. And in the end, we decided to go with the 18 after consultation with the client. And foundation design, very important early step. And lots of weight. Does this compared to our bearing capacity? Our bearing capacity is 400 kPa. We have a worst case of about 223 kPa with all this heavy stuff. And so we're pretty okay from a foundation point of view. Our lateral load, we started out by having concrete walls that gave us a bunch of walls in this direction, some walls here. We're a little eccentric on our loads for that, but we have a way of taking it out with the walls that go this way. And so that was kind of what we started with. And then we went through a bit more seismic as our detailed design worked out. And so we got our magnitude of shear, and we did a quick wind analysis on it and compared the two. And what you'll see here is the wind. The seismic load's about 8 times what the factored wind load is, even perpendicular to the broadside of it. Our seismic load totally governs our lateral design on this. So choosing the structure above grade, we wound up with these levels here. We had several options: concrete beam and slab, concrete flat slab, steel beam, metal deck, wood beams, a metal deck and topping, wood beams with CLT panels and precast concrete. So lots of factors to play for, and capacity, cost, and speed are all important factors. And we went through a variety of options. We figured that wood actually came out at a higher cost than steel. It's not often used in labs. And concrete beam and slab. We have lots of challenges with formwork, which I'll explain in a minute, and concrete flat slab, very difficult to change in the future. And in the end, we wound up choosing steel deck and topping for floors and steel beams. Our traditional institutional buildings up to about 2005 used to be a beam and slab system. It was a good system, reasonably stiff. You could make changes. You could add a hole in here later if you wanted to, quite easily, as long as you didn't go through one of the beams. There was lots of options for changing. We would detail up all the drawings with all the beam elevations. And there were, when I first started out in structural engineering, I wound up doing sheets and sheets of these beam elevations and drawings. Then there's 2 other types of floor system. There's flat slab and flat plate. Flat plate is you have basically a flat slab with some drop panels that look like this. And in 2005, the P3 process brought in flat slab for construction. And it was the cheapest way to make formwork. You don't need to, you run all your formwork through at the same level. It's a lot harder to modify significantly in the future, but if you're doing a P3, you're more interested in the cost for the present than for the future. And so you can, it's economical to build, but it also has some drawbacks. It's a lot less environmentally friendly. Flat slabs use a lot more concrete per square meter than beam and slab systems for concrete, and they use a lot more concrete than do concrete on metal deck or slabs with drop panels. So, so the advantages of steel structure: often no falsework or formwork required, stable for interior use, easy to pass small ducts through your beams, and concrete floors are often placed under roofs, so you don't have a rained out slab. It's non-combustible, and it's easy to attach conduit and pipe racks. And part of the problem is formworks expensive and prohibitively expensive at UBC. And what tends to happen is there's the lower cost area here for housing. A lot of people who are handy with their hands and want to live in an area where they can make changes to their house easily. And so they're living here, whereas the site is out here. And so they drive here for an hour and a half, maybe 2 hours to get to the site. They arrive at the site, they're charged parking, and then they have to come all the way back for the 2 hours here. And in the meantime, there's lots of other sites that need their services. So you have to pay incredibly premium rates to get farm workers out to the site. So, so the result of it is that these institutional buildings at UBC, starting with UBC dentistry, which we did, have become steel structures. And so conceptual design of framing, lots of rules that help you do it. You start off, you've got to figure out what your roof deck span and your floor deck span is for a 76 millimeter deck, which is the most efficient for a beam and slab system. You start out with 2.5 meters. And so you lay out your beams, making sure they've got a 2.5 meter spacing or so. And then you wind up trying to maximize the spacing between the beams to make your system most economical. The next thing you want to do is avoid changing your deck direction if possible. This is a much better system than this is, because you wind up having to change the deck direction, and changing direct direction is always expensive. And so putting joists or beams on the column line is also a very good idea. This is advantageous from a couple of points of view. One is that it helps stabilize the column during erection. The other is that the load from this beam here or joist goes directly into this column, and it doesn't have to go through the beam and transfer through the beam later. So you kind of save in two ways with that. Girders should be at least as deep as the beam they pick up. When you get a situation like this, it might work structurally, it looks funny, and it's kind of poor. You avoid column transfers if at all possible. Column transfers are always expensive. And the other problem with column transfers is the architect's never happy with the depth of the beam here. He wants to size everything based on beams that go here. All of a sudden you're saying, no, I got to have a deeper beam here. So he's never happy. So you really want to try and line your columns up and avoid the transfers, and maybe, do wider spans in the floors above so you don't have to have that transfer. So if we went back to this one, maybe instead of using this beam here, which is picking up that weight, maybe these beams span from here to here, if you really can't have that in there at all those levels. So you want to run the repetitive beams in the short direction. So our repetitive beams here, in this case, are 410 by 39. And in this case, that'd be a 530 by 66. So you wind up saving material. And what we're trying to do here is conserve material. We're trying to make these buildings efficient. We are in a very competitive world. And if your steel or your reinforcing is heavier than the next guy, then the next guy is going to get the job. You want to make sure the mechanical ducts, and there's lots of mechanical ducts and things like that in a project like this. So you want to make sure that they're all framed so the deck has somewhere to go and is picked up here. And so for vertical items of flame, you have to frame them with beams on all sides. And if we started out with a system like this and we wanted to have a duct hole here, we'd say, well, I've got to pick up my framing for this. So I need 2 beams like that would be one solution. On the other hand, that would be a fairly expensive option and probably wouldn't win you too many favors. So you've got to have, that's another way of doing it, and a much easier way of framing that opening. And you wind up with smaller sizes in here, which probably helps if you're trying to get a duct into that space or electrical into that space. And it also means less cost and everything else. So at the edges of forms, you want to put in a bent plate. And this gives everybody a place to attach curtain wall to. It gives a rigid form. Your formwork is part of your permanent structure, and it's useful in your permanent structure as well. So your design must work structurally. You want to make sure that you're not trying to put torsion on open sections. This framing kind of looks good when you start out. You say, oh, I got picked up all my deck at the right places, but I haven't. There's places here where the deck hasn't been picked up at the ends. I'm trying to put torsion on open sections here with these members, and it really doesn't work. And if you look closer at the failure pictures of the Hard Rock Hotel in New Orleans, this is kind of what I think the framing system is on the Hard Rock Casino in New Orleans. Show which beams go through. You don't want to look, your framing diagram should look kind of like this. I can quite clearly tell that these are simple span. And ideally with beams, you're trying, unless you've got a cantilever, you're trying for lots of simple span or moment frame simple span beams. So this was after preliminary design. This was after detailed design, and it's subtle, but you look at those and you say, which one of those do I actually prefer as a framing system? And both of them kind of satisfy the rules. This one there'd been a variety of changes, so that the framing here was kind of at different spaces than the framing up here. And we decided, well, let's just rejig this a little bit. We wound up moving our columns to, in consultation with the architect, made the framing a little more reasonable and laid it out a bit more logically. And this is what we wound up with. So why not wood? Basically, we did a wood conceptual design, gave it to the QS. It was more expensive. And there were lots of other reasons that the owner really didn't want a wood solution, but we kind of had to go through the motions because this is British Columbia. And so you want to design your steel beams efficiently. You find the tributary width. You find the factored beam loading from the load charts that we developed earlier. And then you look at finding which section works best. And what you do is you come in at you found your WL squared over 8 moment. You come in, okay, with this 310 by 52 is going to work, but no, I go up to the top of the table and I look, my 410 by 46 works better, and I save 6 kilograms a meter for the beam. So that's the one I'm going to go to. And so I'm going to try to go for that. And then I go and check the deflection using that simple formula, which most of you should have programmed into your pocket calculators, and off you go. And you find that it's no good. So then you do a linear run through, and you realize that you've got a 10 to the 6 there and a 10 to the -6. So they all kind of disappear. And again, a good programmable solution. And then you go find your I required and go up here, and you try again for the sections that have the minimum I required that are going to make that work, a minimum weight section that's going to make that work. So what really makes your structure economical? Given that you're working with forms and loads that you have only small control over, what can you do to make your structure economical? And the answer is avoid extras. And you want to avoid extras by having well-detailed drawings. You want extra effort and coordination. You want to put in the information required by X16, answer RFIs quickly, think when you're reviewing shop drawings, and cover things that are going to come up with during the construction, like roof anchors, holes and beams, webs for mechanicals. And you want to go through the architectural drawings, make sure C structural items are covered off. And your S16, this clause, provides a really good checklist for going through your drawings and saying, do I have all those things shown on my drawings? And if not, I need to put them in there. And the advantage with that is your fabricator is going to bid tight, and he will add extra to cover himself for things left off if you've left them off, and we don't want them doing that. So the timeline for the stages of the project: preliminary design, we're doing that in 2016, about 4 to 6 months. We wound up with 8 drawings. This was the stage that we had for the tsunami tower. The project gets some funding help here. Somebody you might recognize there came along. And then August 2018, October 2018, we wound up with doing our design development. We've got 36 drawings, and then we go into detailed design. And this detailed design phase was probably a little too short. It was really anxious to get the project going. But one of the advantages was we'd advanced quite a bit in our earlier stages, so in anticipation of this phase being too short. So we actually wound up with less drawings at the end of detailed design than we did in design development. But if you look, there is a lot more information on each drawing. There's a lot more black on each drawing. We detailed the seismic walls. We detailed the brace bay, and the brace bay had actually been a requirement from the development permit application, and we did the miscellaneous metals, and then we did an application for the development permit in 2018, and there had been a variety of discussions that went in before that, but it came back, unfortunately, that we had to do a bunch of changes to the building. The development permit process didn't like the aesthetics, so there were a variety of changes, and some of the elements that we thought were concrete shear walls disappeared, but we managed to bring it out in the spring of 2020 for tender, and started construction. And so off we went. And construction for foundations, there's excavation going on. July 7th, 2020, by October, we're well out of the ground. A lot of the cyclotrons being done. In the meantime, you're overlapping by going through the shop drawing production. Shop drawings are done by the fabricator, but you're reviewing them and to make sure they comply and making little markups and things like that. And then we have our cyclotron construction, October to November 2020, and at grade and above construction. And what you'll see here is that we've used a variety of lock blocks, which are kind of leftover concrete that are used, and we could incorporate these into our upper slab over the cyclotron and add extra shielding with it and reduce the amount of new concrete used, and therefore help try to reduce our carbon footprint. There we are, February 23rd. And then our steels started. I went out a couple of days ago. It had just started, was out talking to the guys that were doing the erection, and also taking some photographs. And so there's our photographs of it. And here, what you will see on this picture here are these funny little diamond shapes. And these are from heat cambering the beams, so that we get, when they add the metal deck and concrete and the self weight of the beam itself, it comes down to being flat when the concrete's placed on. So thanks for being here. I was supposed to finish at 10 to 12, and I think we're pretty much on time. And hopefully, if you don't design similar structures, but you're going to see things that are in your project that you can extrapolate to your work. And it's also, the project like these have many aspects, and it's important to see how the steel design, fabrication, erection fits into the process. And the other thing is that, if we look at our time frame here, we started on this in 2016, and the completion's mid 2022. So there's a 6-year process. So in the time that we've been working on this, you could have gone and got a bachelor's and a master's from U of A, specializing in steel design. And so it kind of gives you a little bit of the time frame. So you're working on several projects at once, because obviously if you were just working on this and then you went on to the next one, A, you'd starve, and B, you get very bored. So you do wind up working on several projects at the same time, and it's nice to see this going along. The construction process of the steel going up is one of the rewards that as a structural engineer, you get to watch your structures being built. And I really recommend working for a firm that allows the people that have done the design to be actually doing the field services. Good. So if there are any questions, I'd be more than happy to answer them in the time remaining.
Awesome. This is really wonderful. Thank you so much, Andy. This has been really great, and the amount of details you've showed us is really wonderful. Great projects, by the way. Before I would like to ask everyone to please send your questions to the chat box, or you can raise your hand if you would like to talk. And I would suggest, if you're a student, please keep your questions to the Q&A session after the presentation. But I'll start us off with a simple question, I guess, maybe. But I did notice you mentioned when you were talking about steel frames that changing the direction will create additional costs. Do you mind maybe elaborating a little bit on those additional costs, what they are, and maybe some detail on that?
Changing, well, I mean, I sort of see there's many sources of why something would change, right? If you've decided that, you know, you're reviewing the shop drawings and you realize, oh, this beam's undersized, I've got to change it out for the next size bigger, or 2 sizes bigger, or whatever. That's one source of a change, and the fabricator, depending on where they are in the process, is going to charge you more money for that. And, you know, maybe he's ordered the steel already, so he's got to restock. There'll be a restocking charge and a reordering charge. Maybe the steel section that you've got is a long lead item, so they've got to rush it out from somewhere. There'll be a variety of sort of extra charges there. If you get further along and they've already fabricated the beam, then, you know, obviously you can't use the old one, so now all that fabrication costs, and that gets comes back from the fabricator. The other source of changes is the owner may decide, listen, you know, I really want to, you know, I want to add extra space here. Let's expand the building in this direction. Or the mechanical engineer decides there's not enough room to fit all the mechanical equipment in, so the mechanical room gets bigger. And, you know, those sort of changes are completely out of your hands, but they will result in changes to structural design. And if that's done after tender, they will come back as an extra. And it's much to my chagrin, it always comes back as a structural extra, even if it's absolutely not our cause at all. So hopefully that answers that one.
Oh yeah, thank you so much. I'm just looking to see if there's, I can see a hand up from Robert. Yeah, go ahead.
Hi, thanks, Andy. Really interesting presentation. Something struck me on the tsunami tower. I, like nearly everybody else other than you, has never designed a tsunami tower. So it was quite an interesting little tour. It struck me that you've got 2 fairly significant competing things going on. One is you want robustness, and the other one is you want to reduce drag, as the way I saw it. So those 2 things seem to be competing in some ways, and I just wonder if you could maybe give us a little explanation about the thought processes from a fairly high level position.
Yeah, I agree, Bob. You've got basically we're designing this job twice. So we're designing our wind and our seismic, and at the same time we're putting on the loads from live load and snow load or vertical loading. But we want to also design for we also want to design the building or the columns so that they can resist this drag force. And what our calculations so far are that the 610 columns that we use, and I got accused of basically trying to transport YVR to Haida Gwaii, but they're kind of the same column sizes. They work out nicely for our design for seismic load and vertical load. Are reasonably good for resisting the drag forces. Now we're looking at if we want to do, and I think this will come out of detailed design, if we want to reduce the drag forces a bit more by adding some steel and maybe some concrete around, steel plate around, so that we wind up with a round shape rather than the cruciform shape, which might sort of tend to be less less able to take the water dynamic forces in a round section. So we'd have the cruciform column inside, and then maybe we would add steel plates on the outside so that you wind up with a more hydrodynamically effective shape to resist the wave forces or the water flow forces and the debris flow forces. Yes, it looks like your detailed seismic brace connections, much of the time in connection design, is delegated to the fabricator. If you are not allowed, that's an interesting question. And one of the things is that by S16, you're not allowed to delegate the design of the seismic connections to the fabricator. You are required to put them on the drawings. And one of the things that we find is that it makes our review of the shop drawings a lot quicker if we detail them up. We have our own software for developing that. We know what the forces are. We're the best able to do that with the software that we have, and it makes checking shop drawings incredibly quick, and it makes it easier for the fabricator to bid the job tightly and reduce costs. So it's a and we put them on our drawings at the conceptual design phase so that the QS can include that in his pricing. And we've actually had an owner who shall remain nameless, but put our conceptual drawings out for tender and got steel quotes on it. And we've completed detailed design and built it. And the fabricator came back later and said, no, I'd like to charge you an extra because those connections were harder than I thought they'd be. And putting in the bolts of the size that you'd shown were harder than I thought they'd be in. And we said, well, what more could we show? I mean, we basically called up what tension we were to tension those bolts to. We showed the size, showed the grade, and the extra kind of didn't go anywhere. I mean, it basically was fully laid out on our drawings what was required, and so good. Any more questions?
We'll give a couple of more seconds to see if someone's typing any question, but feel free to also unmute and
Yeah, why don't you unmute, and then if anybody wants to do a
maybe just a high-level question again about the tsunami tower. Like, who is the owner, and how did you get chosen to do the job?
Well, the owner is the school board, and so they are doing this as part of the school seismic upgrade, and the school seismic upgrade is being done by David Nairn and Associates, and we wound up as the engineers on the tsunami tower, sort of by we understood they were trying to do one of these, and I was up in Haida Gwaii on holiday, and it's a fantastic place to go to. And I contacted the school board, and they said, well, we need a preliminary design for this so that we can get it priced. And I said, oh, we can do that for you. And so we gave them a small fee for doing the preliminary design on it, which actually turned out to be enough to do what we did and produce the drawings that we did, because we had a lot of those typical details from our moment frame work at YVR, and we could come up with a solution that worked, and that was what was put in to the ministry for funding, and the price for that priced by a QS. And so when the job got the funding, they looked to us to do the tsunami tower. So it was very good. They didn't seem to mind that they had a different engineer on the school upgrade than on the tsunami tower. And so there's lots of references to figure out how to design the wave forces, and the key is getting the height that you need, and we've got the height that we need plus a bit more, and it sort of worked out as we felt very comfortable with the design. We looked at a variety of the references that were, I quoted, where did I quote those references? We mostly worked actually through the FEMA guide, this one here that you can download for free, which has lots of useful information. This one here, this came out just a few months ago, and we're also comparing what forces that ASCE recommends for designing of these towers. They're actually building them all over the world. For tsunamis are a problem, not just in seismic zones, but the tsunami can actually wander quite a long way away and cause damage. There was in the 1960s, there was an earthquake in Chile that sent out a tsunami which killed a large number of people in Hilo, Hawaii. In Hilo, Hawaii, which was sort of thousands of kilometers away from where the earthquake actually happened. And in those days, there wasn't quite the tsunami warning system that there is now. The same with the tsunami that happened, the Boxing Day tsunami in Indonesia a bunch of years back, which sent out a wave and killed people in several countries, including as far away as Africa. So the desire is that if your source of your tsunami is reasonably far away, then there are ways of going to higher ground or getting away from the ocean. But if your source of tsunami is close, you really don't have the way of exiting that by any other means than by going to a higher structure and hoping that your structure doesn't collapse.
Mm-hmm. Okay, lovely. Thanks so much for answering those questions, Andy. I think we're about time now to jump to the post-presentation session. For everyone other than the Steel Center students, thank you all for attending. And please keep an eye out for our future presentations. I'll be now taking the students to the breakout room